Okay, so for starters, what do we think of the hackathon? How did it go?
It was good. I enjoyed it.
That was good.
So did you learn a bunch of stuff?
Yeah, I mean, I feel like that was like the first program I wrote entirely by myself. Like not like with the authentication, like because I didn't do that part, but like the other part of it that was kind of cool.
So you didn't write the authentication?
Like I helped with it. We all helped each other, but I felt like I knew how to do the whole program part, so that was cool.
I see. So did it kind of make sense, like what we did in class and here with Firebase? You kind of saw a lot of similarities with that, with how authentication worked, right?
Yeah, for sure.
Okay, so one of the key points to take away from that is understanding kind of these underlying concepts can then allow you to apply those things to all sorts of stuff that hasn't even been invented yet, because every new technology that comes out is built in terms of the old stuff. You know, the kind of the thought process, and every now and then they'll come out with kind of a brand new way of thinking about things. So if you roll back the clock back to like Windows 3.1 days, before all of your times, but you know, we didn't have multitasking operating systems. So when you wrote a computer program, you wrote it to be the only program that was running on that computer at that point in time. You know, starting with Windows 95, you had a multitasking operating system where you can start minimizing programs, and you had 5 or 6 programs running on your machine at once. And we take that for granted today, right? You know, we don't even think about the possibility of not being able to run more than one program on our phone at the same time. Like right now, you put your music on in the background, it's playing, and you're web browsing or reading your email, whatever it is. That just, you know, comes naturally. So even if we think about some of the stuff that we've been doing in here with like the network adapter or the network thread, where we had something happening off of the main thread, we were creating a kind of a separate program, a second program that was running at the same time as the first program, because we had some stuff that was going to be somewhat time consuming occurring in the background, and we wanted our application to still be able to keep cooking. All right, so you know, so back then we made that transition from Windows 3.1 to Windows 95, a new paradigm was introduced, and that was the idea of, as a programmer, we have to start thinking now about doing more than one thing at once, because our computers are now capable of it. So every now and then a new technology or new paradigm like that will pop up where, you know, we're going to have to learn kind of a new way of considering solutions to problems. But most of the time when a brand new technology comes out, a new, you know, API for database XYZ or so-and-so's cloud computing, whatever it is, it's going to be a new thing you're doing, but you're going to be doing it in such a way that's very, very similar to things you've done in the past. Okay, so it's important to understand, not just, it's important, like when we look at the stuff we're doing in here, not just to get things working, but understand why they're working, because those underlying lessons have far more to do with you being able to use tools that you haven't been introduced to yet in the future, as opposed to just getting some little stupid thing working today. Makes some sense? All right, so I want to talk about something here first today. We're going to do two things today. We're going to talk about strings, and then I want to talk about binary trees in kind of an initial setup for like sorting itineraries. But we're just gonna do the first part of that, but we'll talk about binary trees a little bit, and we'll implement one real quick. Or actually, maybe we'll have Shadi implement it for us. We'll have him share his screen.
Oh boy.
All right, so now the lesson I'm going to teach here with strings, this is actually kind of a rudimentary lesson, but it's, as I walked around and I looked at groups this weekend, I saw pretty commonly people using strings incorrectly. So let me kind of give you kind of a crash course on this real quick. So, and we're talking about Java strings here, but this lesson would pretty much translate into most object-oriented languages. Okay, so if I say string s is equal to hello, and I say string s2 is equal to hello, and then I said system.out.println s equal s2. What would print out?
True.
Okay, you think true would print out there? I agree. True would print out there. What if I said system.out.println s equal to hello? What would print out there?
True again.
Okay. What if I printed out system.out.println hello equal s2? What would print out there?
True.
You're kind of just waiting until you step in it. Is that is this like
Yep.
the build up to like the jump scare in the horror movie? Okay, tell me, why are all these true?
They're all pointing to the string hello.
All pointing to the string hello. The question is the way you worded that, you worded it correctly, but I'm not convinced that you know what that meant.
These are all evaluations, so it's a Boolean operation, so it's going to do, it's binary, it's either true or it's not.
Okay, that's why we get trues and falses. I'm cool with that. But why specifically is s equal to s2 true? Is that because they both hold hello?
Oh, I see. I would have said yes to that, but is it because they're both string objects?
Well, here, let's knock that out real quick. So we'll say string s3 is equal to world. So if I put s3 here, this would be what?
I would assume that's false.
False. So it's not because they're both string objects, right?
Okay, so it's the values.
Their same memory address.
Okay. Yeah. So let me throw one more out here to.
Oh, I see.
I'm going to say string s4 is equal to a new string hello. Now you told me that if I say s equal s2, I'm going to get a true, correct?
Correct.
What if I say s equal s4?
False.
False.
Why?
Because it's separate hellos. They're not actually the same.
That's it. That's it. And it's important to understand how this works, and it's more of an efficiency thing. I saw several groups trying to compare strings using the double equal sign, this double equal sign operator. Tell me about the double equal sign operator. What is that guy?
Is it talking about the actual same string, not just like it's equivalent?
Forget about strings for a second. Just tell me about the double equal sign operator in general. Because you've seen that in many cases outside of using strings, right? Where you might compare I equal to 5, something like that.
Is it like strict equivalency and a loose equivalency?
Okay. So I would call this the primitive equivalency operator. Operator.
That works for me.
Okay, this is the primitive equivalency. Oh, I'm missing L's in there, right? All right, this is the primitive equivalency operator. And what it does is it returns true if the left op and right op are identical. All right. So now we have to, actually, let's say this. If they are identical values. So now we have to ask ourselves, what is the value on each side? So when I say something like 5 equal 7, what is 5? What kind of value is 5?
Integer.
So this is an int literal. Is that int literal the same as this int literal? That's what we're comparing in that case, right? If I say hello equal hello, what kind of value is hello? This is where strings are confusing. You remember back when at some point, I'm sure I said it in this class, that almost always the first object you learn as a Java programmer is the string object, but it's also the only object that doesn't act like all the other objects. So let me preheat you a little bit here. What if I say random r equals new random? We've seen this guy before, right? And then I say system.out.println r. What would print out?
Is it a memory address?
It'll print out a memory address. Okay. If I had some other object, if I had made up object r equals new, made up object, and then I printed out r, what would it print out?
A memory address.
Still a memory address. So the value of an object is always a memory address because they're built using the new keyword. Okay. Now, so hello, that guy's a string, right? Are strings primitive types or are they object types?
Strings are object types in Java.
Give me a language where they're not an object type.
Actually, I guess I don't know.
You'll be searching for a while.
Yeah.
What's a primitive type? Let's distinguish these two for a second.
A character is a primitive type.
Yeah, that's an example of a primitive type. So we have byte, short, long, char, float, double, Boolean, right? Those are our primitive types. What would be like a generic definition of a primitive type if we want to understand primitive versus object types? We want to really be able to separate those two. We see them on the street. We want to know, how to treat each one. So what's a primitive type?
Well, with those different, like if it's an int or a char or a double, aren't you going to know exactly how long that value is on its memory size?
There's some truth to that, but that's not what necessarily makes it primitive. So primitives are types built into language that can only hold a value. That's all they can do is hold a value. Objects are types that may be built into the language or may be user defined that can hold 0 or more values and potentially do more, like function stuff. All right, so when we have a string s equals hello, we're certainly storing this collection of characters, hello, in that string. It's probably represented like a character array or something. But strings can also report to us their length. They can give us a character at a specific bucket. They can give us the index of the first location of something. They can convert themselves to uppercase. They can convert themselves to lowercase. They can do all this stuff. So would it be fair to say that in this comparison here, strings can do a lot more than just hold a value? So strings fit into this object type category. All right, now, this is where things get a little bit weird when we're looking at strings in Java, because Java's given us this nice friendly syntax with strings. So let's take out this world thing here for a second. So notice string s equals hello, string s2 equals hello, string s4 equals new string hello. This is your common way of defining a object, correct? That's how we define objects. We always say object type, variable name, equals the new keyword, object type again, because we're making a call to the constructor, and then whatever parameters that constructor takes. So every object except for strings, you would always build this way. Using this syntax, you replace the word string in both these places with whatever the object name was. Okay? But strings, because they're so common in Java, and because they're so common in most programming languages, they actually have this special format. I call this syntactic sugar. So this is a shorthand for writing something like this. All right? But it's only almost equivalent. They're not actually identical to each other. All right, so what if I said string S5 is equal to new string hello? And I were to print out S4 equal to S5. What would the output here be? This line right here. False. You think false? Okay, that's correct. It is false. So let's talk about why. Now you told me that S equal to S2 is true. You've told me that S equal to S4 is false. I assume S equal to S5 would also be false? For the same reason that S is not equal to S4?
True.
Okay. So why is S5 not equal to S4? They were built the same way.
Because they're pointing to new memory addresses, right?
Okay, that's true. So every single time we use the new keyword, a memory address is created. So when we use the new keyword, we are specifically telling the operating system we want a new chunk of memory for storing this guy. So if I were to print out S4's memory address, it would give me, if I could get to it, I actually can't get to it because he's already overridden the toString method, but if I could get to it, I would see a different memory address than S5 has. And I would actually see a different memory address than S2 has. But S and S2 both have the same memory address. Why do you think that is? Because comparing S and S2 to each other did give me a true value. Why do you think S and S2 held the same memory address while these guys held different memory addresses? I kind of already explained why these guys hold different memory addresses, right? I said every time I call new, I'm explicitly saying give me a memory address. But why do these two guys accidentally get the same memory address?
Is there like a master, like a string singleton that's an array of strings, so to speak? So it's like the same instance of the string, and it's just like you can stuff a bunch of strings into that instance thereof?
Yeah, I think you're onto something here. So we have this string system literals. So this guy is a collection of global, well, really we could say system literals. I'm specifically talking about system string literals, but let's actually just call them system literals for right now. So a collection of global values that are constants within the current runtime. So some examples of the system literals would be things like 1 and 2 and 3 and 4 and 5, blah, 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 blah. Integer literals, right? Things that are numbers. Can Java make a pretty good assumption that the number 5 exists before you start coding? That's a thing. We could also have all of the Unicode mappings in here. So if you store the letter A, the character A, it would map to the underlying Unicode character. These are literal values that we're not inventing. We can't get into our program and say that a 5 is now actually equal to a question mark. We can't redefine these guys. A number is a number. Okay? But then we have these string literals. And at first, this is empty. But as we start doing things like string s is equal to hello, what it does is it says, okay, do I already have a string inside my literals that's hello? If I don't, I'm going to go ahead and create that. And that guy's going to have a new memory address. So this dude will live somewhere in memory. All right. But now, when I create my string S2 and say hello, it's going to first check with my global literals and see that I actually already have a match. So rather than taking up twice the memory space for storing the identical value, I'll actually just have S2 hold the same memory address as S held because I already have that value there. Does that make sense? So maybe this is that memory address ABC123 or something like that. We'll make it look hexy. So that's the memory address where that guy lives. All right. So actually the value of S would be this guy. That's the actual value that's stored in S. It's a pointer to that memory location. And the value of S2 would be that guy. But now we went in here, we said string S3 is equal to a new string. Hello. Because we explicitly use the new keyword, which is how we do things for every object, but most of the time with strings, we are specifically using the simplified syntax because it's more convenient. But I want to drive home the point that it's actually not 100% identical. In this case, I am saying I want brand new memory. I don't care if you already have a literal named hello. I want new memory. I want fresh memory for this guy. So it's not going to go in and add this new literal or find the old literal inside my string literals. Instead, it's going to create a brand new string, hello, and maybe this is at 2 or 12F C4 hex, something like that. I'll make the C capitalized. Something like that. So this guy lives at that memory address. So that's the actual value that S3 holds, is that memory address. So that's why S is equal to S2, because they both point to the same literal memory address. But S does not equal S3, because S3 was built with the new keyword, which says, I want fresh memory. That's someplace else. Does that make sense? Now, the punchline for all of this. Never use the double equal sign for comparing strings unless you are specifically testing for these being the same exact string at the same memory location rather than having the same contents. Usually when we're comparing strings to each other, we're asking, do these two strings match each other in terms of their contents, right? So if we're doing that, if I have my string S is equal to hello, I have my string S2 is equal to hello, I have my string S3 is equal to new string hello, S equal S2, we already said is going to give us a true. Steal this. S equal S3 will give us a false. But S dot equals S3 will give us a true. So the string class has an instance method called equals that compares the contents of the calling string to the contents of the string you pass it. So in this case, S dot equals S3 is true because they both hold an H followed by an E, followed by an L, followed by an L, followed by an O. All right, now this guy is case sensitive. So there's also a dot equals ignore case.
We actually use the s dot equals in our code during the hash.
Yeah, but the reason I brought this up is several teams, at least 3 that I saw, were using double equal signs for comparing strings. And what's dangerous about that is depending on what strings you're comparing, it might work, but it works for the wrong reason. So you might get lulled into thinking, oh, this is how strings are compared in this language. When actually it just happened to work because of the specific strings you were comparing. Now I'll show you what I mean by that. So, so s dot equals ignore case s3 would give us a true. So in this case, if I changed this guy to a capital H, this line would now boil down to false because s is not equivalent to s3 because one has a capital H, the other one does not. Whereas s equal ignore case s3 would be true. That make sense? So let me go back up to this guy here to explain why you could get that, what I'm going to call a false positive, where when you write the program, you're like, well, it worked. If you say, if s is equal to hello, this is true as well. And why is that? This looks a lot different. When I say s is equal to hello, that looks a lot different than saying s is equal to s2. Right? At a glance, that looks different. But what's the reality of the situation? What is S2? If you had to concisely tell me what S2 is, what would you say? What's the simplest way of telling me what S2 is?
It's a system literal.
Okay. What is it before that?
A variable?
The variable. Okay, so S2 is a variable. And what do we do to variables? Regardless of what kind of variable they are, what happens to variables when our program runs? No matter what kind of variable it is, when our program runs, our variables resolve to their value, correct? What's the value of S2? It's a memory address which ultimately points to a string. Don't these guys look identical now? Because actually this is, S would boil down to hello as well. And so would this S. So after the program's running, that's what those 2 lines ultimately look like. Is hello equivalent to hello? Is hello equivalent to hello? Is this system string literal the same value as this system string literal? Is this system string literal the same as this system string literal? The answer is yes to both of those. That's why saying S equal to hello and S equal to S2 boil down to the same value, but it's not because it's not because their contents are the same. It's because the location of this literal is inside our system string literals at exactly one place, so that we're not wasting a whole bunch of extra memory for holding the string literal hello. Whereas S3, we've purposely said, I don't care about you wasting memory. I want new memory for this. So you'll give me new memory, and this is what I'm going to store there. We'll put it back down to a lowercase h. So at that point, when we say S3, S is equal to S3, like I said before, I'm resolving it down to its actual string, but this is actually saying something like 0x123abc. Is that equivalent to 0x, whatever I said, a 4fc2 or something like that? These are clearly not the same memory addresses, right? So that's why that is false.
And so string literals, they're case sensitive as well. So if S2 was an uppercase hello, it would get a new string.
Correct. Yep. then they would not match. That would be a different string literal address. All right, so the value of any kind of object, the direct value before we follow the pointer, is always going to be a memory address. So when we use the primitive equivalency operator, what we're doing is we are comparing the value of that variable. And the value of any object is the memory address where that object ultimately lives. Because object variables are pointers to someplace in memory. So when we use the double equal sign here in Java for this, same thing in C#, it's comparing the memory address of the first string to the memory address of the second string. And if they're the same, it'll give you a true. Now that also means they must have the same content, okay? But it's not looking at content here. It's saying, do they live in the same place in memory? Okay? Now, you do need to be careful with this though, because you might say, and the reason why a lot of programmers at the hackathon were using the double equal sign for comparing strings is because in many languages, you can accurately compare strings with the double equal sign. So for instance, Python will do that. The default version in Python 3, when you use the double equal sign, they've overridden the double equal sign for strings such that it will compare the contents of the string. That isn't to say that basically what it says is in Python, you can't compare one string to another in terms of their memory address. You've lost that ability because they've defaulted it to compare strings by what's called lexigraphically. So that's alphabetically based on Unicode. But it would technically also work for like commas and things like that. So it would determine a lexicographical value for a string with question marks and commas and exclamation points and stuff in it compared to another one. So like hello exclamation point and hello. I'm not sure which one's less than the other one, but one of them is because of the lexicographic value for it. So it's not quite alphabetic like we would use, but it's a thing. So Python's taken that decision away from the programmer and said, look, if you're working with strings, you care about content, not location. So we're going to make life easy for you by saying we re-implemented, we overrode the double equal sign specifically for strings to allow it to compare two strings in such a way that you likely need. And you mean the contents of those strings.
Would a language like Python, because it's loosely typed though, could it implement something like system literals? Because you don't know what you're going to get.
Yeah, I mean, you certainly you could, because I mean, it's going through it line by line. So as it hits something and it checks the interpreter whether your system literals would just be an array of strings, and if it finds it at bucket 4, it says, well, I'm not going to redefine it. I'll just use bucket 4 now for that guy. So yeah, from a language creation perspective, it could certainly do it if it wanted to, and that's how objects work. So I mean, if you take two Python objects and you compare them to each other, I promise you, it's comparing the memory addresses just like I'm explaining here. But Python treats strings differently, just like Java treats strings differently. And Python kind of made the executive decision that to go ahead and override the default meaning of the double equal sign, the equivalence operator, for strings so that it compares strings in such a way that, if we're being honest with ourselves, it probably is extremely likely that the programmer wants to compare the contents of the strings.
Right, so it's a matter of language implementation. Then how did the language designer decide to implement equality operators?
Well, right, but see, but that's the thing, is the equality operator. So here, let's throw this on another slide, because I mean, you're exactly right, and that's kind of gets into getting to the crux of what we're talking about here. So how did the language dev decide to implement equality? So we'll just use the equal sign as our equality operator. So we have primitives, we have objects, Now, if we just stop there, everything's cut and dry. We're good. Primitives, we know where they stand, right? Those are our, string our int literals, our char literals, our Boolean literals, floats and doubles. They make sense to us. Those are not memory address things. Those are literal values. Objects, these are always memory addresses. So these are literal values. These are memory addresses, always. So if I'm using this equivalence operator and I'm comparing two primitive types, I'm comparing their literal values to each other. If I'm comparing two objects, I'm comparing their memory addresses to each other. If it stopped here, it's cut and dry. Okay? But then we have this jerk that we just happen to use a whole lot in our programs called a string. And strings are used as often as primitives, yet are technically objects, because strings can do more to themselves than just hold a value. So now you have to decide, do we treat them from an equivalence perspective like primitives, or do you treat them from an equivalence perspective like objects? Java treats strings as objects for double equal sign. Python treats strings as primitives or double equal sign. You can make an argument either way, right? But it does have an impact. So this double equal sign is something to be careful of when you're moving between languages. So one of the things that I teach with programming is that all languages are the same. You just have to learn the little caveats between the languages. And 90+% of the time, that's true. You can, for those of you at the hackathon who had 200 students in your group, and maybe you had never seen Python before, for an example, you probably pretty quickly got up to date on Python and saw that, oh, there's a lot of stuff that's pretty similar here to what I've been doing in Java, right? And you just had to figure out the little quirky syntax, how Python puts the colon at the end of the line, and indentation is really, really important, and that kind of stuff. But for the, 80–90% of what you were looking at, you pretty much could follow, right? Had any of you never seen Python before the hackathon? I'm assuming at least a couple of you hadn't seen it before or worked with it very little. Okay, but if it wasn't Python, you could replace Python with some other language you hadn't seen before, and I can promise you that your knowledge of Java or whatever other language you've been exposed to will allow you to read large portions of that other language, even though it's brand new to you. You have a way better fighting chance than with our natural languages, where I know English, so if somebody threw a Russian book in front of me, it just looks like just gibberish to me. I think it looks cool, but it's just gibberish, right? Programming languages, we have a much better fighting chance of taking a single core language and being able to have a pretty good understanding of any language we're looking at, even if it's the first time. But where we do need to be careful is in situations like this, where we're kind of at the mercy of the language developer when they had to make an executive decision. Okay? We expect every single programming language to have an equivalency operator, because Boolean expressions are a really important part of programming languages. Why? We go back to that beginning thing of how do human beings solve problems. We remember stuff, we ask questions, and repetition. And asking questions really requires us to be able to see if two things are equivalent. It's a pretty important piece of being able to ask questions. All right, so that's going to be in every single programming language. With that in mind, we're at the mercy now of the program designer to decide which column this guy fits into. Is a double equal sign a primitive type? Does it behave like primitive types for strings, or does it behave like object types for strings? Java treats them like objects, so it's comparing memory addresses. Python treats them as primitive, so it's comparing the underlying value. It's re-implemented the meaning of double equal sign specifically for strings. If you are, if you write your own Python program and you want to override the equivalence operator for Python for your specialty object, all you do is you create a underscore EQ self function. You rewrite this, and then you can define what it means to compare one of your dog objects to another dog object. You can define what that means. So in Python, the programmer has the ability to override that. And actually in C++, the programmer also has the ability to override it. With generics, you can actually kind of pull this off in Java. But what I'm saying is that decision was made for you with strings. So that's kind of the deal. So I think you kind of got to the crux of this, where we are at the mercy of the language developer, and this can be one of those things that throws us off, because we see double equal signs pretty often in programming, because that's something that's left over from C. And what I'm telling you now is that it doesn't always behave identically, depending on which language you're working in. You have to figure out how the programmer decided to make it work for strings. All right, so from a Java perspective, this screen, you're all going to say in Java, never use the double equal sign for comparing strings unless you specifically are testing them for being the exact same string with the same memory location. All right, is that clear for everybody? How that stuff works? Okay, so secondly, I want to set us up for post-Easter break with binary tree stuff. So we will go through that and implement one. So we are good to go post-Easter break. Okay, what can you tell me? Hopefully we've all at least heard the phrase binary tree before. For those of you who have undergrads in computer science, you better have heard of binary trees before. But most of us at some point have at least probably heard the phrase, even if it just came up in a book somewhere or something. Well, who could tell me what a binary tree is? And unmute yourself if you're just talking to your monitor.
Is it a tree where each node at most has 2 children?
Okay. Yep. So what's a tree?
Oh man. It's a structure that starts at a root level, and then so you're going to have a parent, and then you're going to have 2 children, leaves basically. And so
what's a tree relative to a linked list? Because we've done linked lists in here, right? So a linked list compared to a tree, what's the difference between those two?
a linked list, you only have one child, I would say. So each parent has one child in a link. Or I guess that's not the right way to think about it, but the nodes are all chained together. One node leads to the next node. Yeah, thanks. Linear.
Yep. So linked lists are linear, trees are nonlinear. All right. And if we want to think about this in terms of the human world, a line is like a linked list, and we could say a tree is like a tree. All right. That's why they name it tree. All right. So if you walk outside and you look at a tree in your yard, to get the data structure version of a tree, you just flip that tree upside down. And that's what trees look like in data structures. So instead of the root of the tree being stuck in the ground, it's actually pointing up in the air, and the rest of the tree kind of hangs from it. That's the way we usually show trees. But a tree is a tree. It's non-linear. When you're looking up at a tree, unless that thing's been pruned to hell, you're likely looking at something that has branches coming off it left and right, correct? And then there's leaves all over the place and stuff like that. It's a very complex situation, as opposed to a linked list. This is a line or like a string, something that's or like a water hose. It's not overly complicated. It's just kind of a pretty simple little thing that's just laying there, right? So we're dealing with, when we talk about binary trees, we are dealing with the difference between linear linked data structures and nonlinear linked data structures. Now, what is the, well, trees are an example of nonlinear linked data structures. I'll give you, anybody know any other, so we'll put binary tree in here. Anybody know other nonlinear linked data structures?
Isn't a heap?
Okay. A heap technically would be implemented, probably would be implemented as a nonlinear linked data structure, but doesn't have to be. What is a heap? Or is it just a cool sounding name?
It's been a long time since I figured out what that was.
Well, the good news for you is most people would just say it's a cool sounding name. It's one of those tech terms that kind of, you're like, well, it's just, you know, toss that on top of the heap, right? Like, what does that even mean? You want to take a stab at it?
Well, if I remember right, it's associated with a binary tree. So, I mean, it's got child nodes that come off of kind of a single root.
Yeah,
right?
you're talking about a potential implementation for it. I'm talking about its use. What is the use of a heap? What problem does a heap solve?
Oh, all of these are looking at time, right? I mean, it's how fast you can get through data in a certain amount of time. Searching, yeah.
I'm going to say searching / sorting-ish. That'll make sense when we talk about here in a few minutes. What problem does a heap solve? It's actually a really common problem, but you're in good company. In fact, you've already done better than most, where you kind of have like a sort of an idea of what it does, but it actually solves a really easy problem and something that's really common and something that humans do in real life. But I'll give you another 4 seconds on it. Otherwise, I'll just tell you.
Nah, go for it.
All right. So this is a priority queue. All right. So a heap is what you get at Disney World now when you buy, I guess there's like a special pass that lets you jump the line. And then there's the normal pass where you got to wait in the long lines. So people that have the special pass, they get priority.
Like Disneyland.
So they can cut right to the front.
Called a fast pass.
Yeah, fast pass, that guy. I've been to Disney several times. In fact, I got engaged to Disney World a few minutes ago. Yeah, it was a few minutes ago. But yeah, so I haven't been there since they've had the priority queue, the fast pass thing. But my brother told me all about it. He's got 2 young boys. But in any case, you know, a priority queue is used all over the place.
I knew that because I'm a dad, so it's
yeah, I get it. Yeah, that's how I knew about it, because my brother told me about it. But so a priority queue is used all over the place in operating systems. You know, when things are getting scheduled on the CPU, certain things are just flat out more important than other things, and even though they just had CPU time, they're going to cut the line and get CPU time again because they're higher up on the heap. They have a higher priority. Does that make sense? So we use heaps all the time. So it's an automatic way of ordering. So the nature of a heap is an automatic way for ordering things in a line, given the additional qualifier of priority or importance, something like that. You know, we don't use a heap at McDonald's, right? You walk into McDonald's, it's first come, first serve, unless you get you start doing the creepy, I'm a fat, hungry guy, and then you probably can jump a couple of spots just out of weirdness. But, you know, in general, it's human version of a line at McDonald's is a linked list, an array. It's a line. It's just a normal, flat-out queue. Okay? A heap says we're going to give importance to certain people in line. All right, and as you said, heaps are often, historically, heaps would have actually been implemented using a linked list. and you certainly could. You can use a linked list, well, you've used a simplified version of a linked list called a queue. We looked at stacks, which are just simplified versions of linked lists, right? And we see queues are also simplified version of linked lists. We only need to be able to remove from the front and add to the end. That's a queue. So you can create a queue data structure, and then when something gets into the back of the line, we could then add in it. Adding to the end could actually have a little bit extra logic in it, where we could advance him forward in the queue until he's positioned where his priority allows him to be positioned. It actually isn't all that hard of an implementation. We could also implement it as a binary tree, which we'll see as we keep talking about the stuff today. Ultimately gets us into this situation where our data is already in kind of an organized format. And once something gets processed and leaves it, we drop it back in, it kind of gets thrown back in to an organized process. So it's probably more efficient over time to implement a heap using a tree structure rather than a linked list type structure. But that doesn't really define what it's used for. That's just more of how it's actually built under the hood. From a user's perspective, a heap solves a problem. I toss something in, and the things that come out of the heap are going to be the next most important thing for whatever it is, my CPU, whatever. Okay, so we have binary trees, we have heaps, and I don't have a problem putting heap in the nonlinear linked data structure column. But this guy would be more of a borderline thing, because it depends on implementation. What else? Here, I'll throw our n-ary tree in there. So this kind of, before you mentioned that with binary trees, these are, they have at most 2 children. N-ary trees have 0 to n children. So we take off that limitation on the number of children a node can have. I'm not going to talk anymore about that right now. We have things like AVL trees. I'm going to say AVL / red-black trees. Have any of you heard of either of those?
A long time ago.
You're talking some serious Greek to me right now.
Okay, good. Oh, you were at Bible study today, right?
Yeah.
Yeah, so tell Maddie how everybody was cheering at me.
Oh, you mean when you wanted to go back and do the peg thing?
Oh, no, I didn't even tell her that one. Yeah, that was at the beginning.
I thought Pastor Smith was calling you a child at that point in
Oh,
Avails.
yeah, that was pretty fun. He didn't know if he was going to be able to cover Samson in 3 or 4 weeks. So he said, well, if we finish it in 3 weeks, then we'll he has the backup plan to do something else. So I said I wanted to do JL, Jael, who was the lady with the tent peg in her hand. Oh, that was awesome. Oh, the thing with the angel of the Lord. When they
and then you said it was Jesus?
Yeah, like loudly. And oh, yeah, it was awesome. And then remember you saw the word awesome in the Bible?
That's true. And then everyone laughed when that guy read it.
Yeah. See? They all laugh at me when I say things like that, when I say things are awesome in there. Like, oh, it was just a little kid talking. But no, it's in the Bible, people. All right, so AVL and red-black trees. Anybody know what those are for?
No idea.
Is it a sorting thing?
It's related to it. So these are self-balancing trees. It could be related to sorting. It probably is more related to database.
Yeah.
So AVL red-black trees, these are self-balancing trees. And the
I have to be
idea
here. I'm a DBA. Blast. I'm a DBA, so I should know what that is. Blast.
Oh, not necessarily. I mean, DBAs are users of, I would say a DBA is more of an IT position than a computer science position. Your general, 75% of your time, you're using this database tool, database management tool at a professional level. And then 25% of the time you're writing little stored procedures and things like that to solve problems. But in general, you're an expert of the database management tool, right? So it's not really your job to be able to build a database management tool.
Correct.
So you wouldn't necessarily have to know how they're implemented under the hood, as long as you could, as long as you could drive the car. It doesn't matter if you could have built the engine.
Fair enough. Fair enough.
The idea is self-balancing trees. When you're doing tree searches and tree traversals, the taller a tree is, if you have a tree that's very long on one side and short on the other side, we would say the tree is out of balance. So you think about out in the wild, you might see a tree where all the leaves and stuff are all on one side. Maybe they've cut part of it to like make room for power lines or telephone lines or something like that. And over time, that tree actually starts like drooping because it's not in balance, right? It's one side's a lot heavier than the other. Well, if you were looking for something in a tree data structure and the thing you were looking for happened to be on the short side, let's say, and you started looking on the long side, you're going to spend a whole lot of time searching for something that you'll never find on that side. And then you finally get back to the short side and find it pretty quickly, but you've wasted a whole bunch of time. So the idea is that a balanced tree, so a tree that roughly has the same number of branches or whatever on each side, is going to be more efficient, where when you're searching for something, your average search time should be much more predictable, something like that. So AVL and red-black trees are kind of common algorithms for maintaining a balanced tree, where every single time we add a new element to the tree, it rebalances itself, so it's always in a state where it can be quickly searched, or quickly searched is maybe the wrong way of putting it, where it can be it can be searched in a predictable amount of time, something along those lines. Let's see, any other? Oh yeah, we're not even okay. Any other nonlinear data structures? And actually, anybody know a use for n-area trees? Syntax maps are kind of your biggest use of them, because you lose a lot of utility with n-area trees. And we're going to talk about binary trees, so we're going to talk about the simple version of this. But with n-area trees, you kind of lose the special sauce of a binary tree, where things are stored in a very in an ordered way. N-area trees don't do that. They basically just say, look, I'm going to take your symbols and I'm going to store them in a map that is equivalent to the way you gave them to me, but it allows me to store individual tokens differently. That's pretty powerful for syntax maps, equation editors, stuff like that. Okay, other nonlinear linked data structures, moving away from trees. So far, these are all tree-typed data structures, with the possible exception of heap, depending on implementation. So anything that goes beyond trees that you're aware of? What if I gave you a map of Wisconsin and I said, I want you to build a data structure that can hold, that can represent this map of Wisconsin? And we kind of said our nodes are like the, like Grafton would be a node, Mequon would be a node. So our cities, towns, those would each be nodes. What kind of data structure would you use, or could you create to store data about the various nodes in Wisconsin and how they're linked to each other?
A graph.
Graph, good. So we have our graph data structures, and these guys, so we can think about this like storing a map, something like that. We have a couple of different types of graphs. We have directed and undirected graphs. I'm not going to get into that. There's a whole area of math. Actually, Shadi, you should have known this. There's a whole area of mathematics on graph theory. Was he just crying in a corner now?
No, I said like, I am crying because I don't really remember that much from it because it's been a while. But
You know you had it.
yeah, I know I had it though.
Okay, so really, Maddie should and Ani, they both had the class. Well, Maddie had the class twice. She had data structures, and she was a math major, so she had the graph theory stuff too. Didn't you have graph theory?
I definitely don't remember taking any classes about graphs other than 490.
We did stuff in discrete mathematics. I think we did a little bit of graph theory, and then I think geometry we looked at just a little bit of graphs.
Maybe, yeah.
Okay.
I
Yeah,
took discrete too, and I don't remember graphs.
yeah. I usually only get to graphs in data structures if we have time at the very end, but I usually at the very least introduce the next thing, which is a famous computer science problem. That's the
Traveling salesman.
CSC. So the traveling salesman problem. Do you know what the traveling salesman problem is?
Oh yeah.
Yeah, we learned about this in Locklear's class.
Yeah. So it's a famous computer science problem. You know, so the idea.
Now I know why I couldn't remember it. It's because it's the darn Dudney book. That's why.
The which book?
Dudney. I hate that book. That book that Locklear uses for that class. That
Touring Omnibus.
Shut up, Shoddy.
Isn't that what it is? It's the Touring Omnibus book, right?
Yeah.
Yeah,
dude,
it's by
Turing
Judy.
Omnibus and another one. Actually, we had trees, and all I could think of is like, how could I use this tree to generate a context-free language? That's all I could think of during our tree discussion. I was like, oh, twitching.
Yeah, so right there, N-ary trees.
Yep.
Yeah. So traveling salesman problem, you know, computationally expensive problem to solve, and says, hey, we need to, you know, I'm a traveling salesman. I need to visit all these towns to do my job. I want to visit them in the most efficient way possible to save money on gas or, you know, time or, you know, whatever it is, however you want to think about it, optimizing your job. So we're going to use graphs to figure out if I have my home base, how do I travel to each of those cities and return home in the cheapest way possible, whatever cheap means to you, if it's time, if it's gas, if it's whatever. And we use directed graphs as the base data structure. And then I'm guessing when he talked about it, would you guys use min-max trees?
Yep.
Yeah, so effectively what you did is you took a graph and you kind of exported trees from that graph. So a graph is a collection of tree data structures, and some of the nodes in those trees connect to nodes in other trees. So you could export that from, so the min-max tree effectively gives you a collection of trees, but you derive it from the graph, which we can think about as a directed graph would be like a map. Actually, this would be we call it an undirected graph, sorry. It's like a map of Wisconsin. You can take Interstate 94 east, you could also take it west. So that's the edge between, let's say, Madison and Milwaukee, even though I know there's towns in between. But if you treat that as those are two nodes, we have one edge that goes in both directions between those. All right, and this would be a nonlinear type of problem. So that's kind of a famous computer science-y problem using nonlinear data structures. Well, so we've kind of introduced this concept now of nonlinear data structures, that is, things that have more than one child. A linked list would have one child. These guys have more than one child, so they are nonlinear. Cool. Now let's specifically talk about binary trees. So binary tree has a single root node. Each node has at most 2 children. Nodes with 0 children. So if we think about with trees, if we think about things that connect to the children, we would call those branches of the tree, right? Okay. So if we had a node that had no branches coming off of it, what would we call that node?
A leaf.
A leaf.
Called a leaf. That's the leaf of a tree, right? Okay, nodes with 0 children is called a leaf. Are called leaves, whatever. There. Now we're correct. Okay. So this is, and now we have the special sauce. That is values to the left of a node are less than or equal to that node. Values to the right of a node are greater than that node. That's the special sauce of binary trees. Our data is stored in a way that allows us to maintain order if we choose to. All right,
Question.
go ahead.
So for binary trees are what allow binary searches to happen then because the data is ordered?
The data,
Yes.
well, sort of. Traditional binary search would actually be done on sorted linear data. Sometimes it's called a dictionary search. But if you were to search a binary tree, you're technically doing a binary search, but it's not the traditional dictionary algorithm because it's using the special sauce of the binary tree to accomplish this. But under the hood, you are performing a binary search.
Okay, it's just the data structure. You just traversing the tree. You already have that.
Correct. Yeah. So here's the deal. The traditional binary search, like I mentioned a second ago, sometimes called the dictionary search. The idea is that if you pick up a dictionary, you start off with the assumption that that dictionary is sorted. Correct. Dictionaries would not be very valuable to us. Well, we can say they wouldn't be very valuable to us if they were not in order. If I'm looking for the definition of apple, I know that's going to be towards the front of the dictionary, right? That's really less true than it used to be because now we probably, I don't even remember the last time I actually used the dictionary. You just go to Google and say define apple, right? And it gives you the answer. So who cares how hard Google had to work to go, to go and get it. So, but if we roll back the clocks to yesteryear, before we had the internet and all this stuff, it's certainly helpful for us to have a dictionary that is in order, right? So the way a traditional binary search would work is we have a collection of data that is presumed to be in order. And then what you would do is, let's say I'm searching for apple. You would actually just go to the very middle of the collection and you put your finger down on whatever piece of information is in the very middle and you'd say, is this the answer? Is this what I'm looking for? If I'm in a dictionary, I'm in the middle. I'm probably in like the M's or something like that. You would say, no, this is not what I'm looking for. Is the thing I'm looking for come before or after this? If it came, so in this case, I'm looking for apple, it comes before it. So I'd rip off the back half of the dictionary and throw it away. So now I have half of my dictionary. Then I turn that to the center. Put my finger down, is this apple? Nope, should apple come before or after that? It's probably gonna be before that. Do that several times until you finally land on apple. So you keep having your data over and over and over again. But it starts off by presuming your data is already sorted. So if you have like a linked list of airports and we want to efficiently search through that linked list of airports, we would first want to sort that linked list of airports in alphabetic order, something like that. Effectively put it in dictionary order so that we can then go and perform a binary search on it and not have to check potentially every single value in there. Right now, we're being inefficient. Right now, we have this giant list of airports, and we do a sequential search on that list of airports. If I type in MKE and I'm filtering on it, what do? I just zip through my linked list of airports, and I pick out the ones that have an MKE in them. And I don't care about the speed. I just say, oh, this just works. Whereas a binary tree, its special sauce is such that when you store data into a binary tree, it naturally gets stored in order. It gets stored in a format that that is searchable right off the bat. Okay? So it allows us to always assume the data is in a searchable state. Let's look at a picture of a binary tree.
During the hackathon, John was telling me about their little word game app, and he's like, it's slow searching. I was trying to explain to him what a binary search was. I did a really horrible job. I was like, oh, if you just use a binary search, you'll get your stuff fast. But
well, he was also bringing it in from a file.
Well, even still, like using, I guess if it
file IO is probably the slowest IO you have on your computer.
Yeah, I was gonna say if it
the only thing that would have been worse historically, well, he was doing file IO off the hard drive, and I think those machines still have mechanical drives in them. So he was doing file IO off serial
disk.
mechanical. Serial ATA over solid state drive would have been faster, but still slow relative to RAM. But if you want to go back to historical nightmare, if you was on a floppy disk, 3.5 inch or a 5 1/4 inch floppy, or even go way back.
Tape drive.
Yeah, the giant, record size floppy disks. File I/O is extremely slow, and you're not going to get any faster than a solid state drive with it, which is fast relative to extremely slow, but is always going to be way slower than RAM. So hard coding the data into the program one way or another makes it a lot faster to search. And actually, what you should have done is, I don't know if you did this, every single time they typed in a word, did you search your actual whole file again?
Yes, I did.
Okay, yeah, so that was stupid.
Well, I was banking on that. I knew we needed a better system to do that. I just didn't know, we didn't have the time necessarily to implement that. Well, we had the time, I just didn't know how to do it. So.
Okay, yeah, so we just backtracking on it a little bit. What you should have done is, as soon as your program launched, read everything in from the file into a linked list. Done. Now you have a local RAM version of your words. You can just search through it every single time I type something in. It'll be fast. So read the file once, get it into your program. So, right at the beginning of your program, there might be a little hiccup because it's reading in whatever your 4 zillion things are. You could even throw it on a separate thread if you want to, because chances are you'll finally have it all read in before the person using your program actually starts entering stuff. It's kind of like a race. But once you have it in linked list format, you have it in your program, now it's stored in RAM. And who cares that linked lists are technically inefficient from a speed perspective? They're way faster than doing file IO any day of the week. So it would feel pretty immediate to search through a link. And it'll be even quicker if you sorted that linked list and stored it into a array. And it'll be even faster if you, instead of a linked list, you use the binary tree. All right, so we'll see that today. So there's 2 ways you could have upgraded that. All right, so I'm just going to create some Legos here.
Well, and so like on a search engine, is that usually what they use, like a binary tree then?
Oh, well, good. So there will be trees involved, but there's a lot of other stuff involved there as well, because it's having to do keyword matching and sanitizing user input data. Because you're typing in this like really random long sentence, searching for something. It's trying to figure out what parts of that are important and which parts of that is just crap.
Yeah.
But trees are involved. All right, so these are just like, I just have puzzle pieces sitting over here to the side. So let's say I start off with a 5. So here's my binary tree in the middle. It's currently empty, so I'm just going to drop my 5 right there at the top. That's my root node. All right, so now I'm going to put a 2 onto my tree. So I drop the 2 onto the top of the tree. Now, right off the bat, there's no room at the root of the tree. So that place is occupied. So the question then gets asked, should a 2 go to the left of 5? Is it less than or equal to 5? Or should it go to the right of 5? So where should 2 go? Is 2
Left.
Left.
Okay, 2 less than or equal to 5. So first thing we're going to do is we're going to say, well, does the root node have a left child? It currently does not. So we'll just set our left child equal to that 2. All right. Next, let's place the let's place the 1. So we'll drop the 1 in. This place is currently occupied. Should the 1 go to the left or should it go to the right? It should go to the left. Does this guy have a left child? Yes, he does. So what are we going to do? We're going to pass the buck. We're going to ask this left child to place this 1. So we just pass him here. Okay. Should a 1 go to the left or to the right of a 2?
Left.
Go to the left. 2 currently does not have a left child, so we'll just place this guy as his left child. Okay, now let's do the 7. Drop the 7 in. This place is already occupied. Should a 7 go to the left or to the right of this guy? It should go to the right. This guy does not have a right child, so I'll go ahead and place the right child there. I'm actually going to spread these out a little bit here, just so now we'll place the 8. No room here. Should it go to the right or the left? It should go to the right. No room here. Should it go to the right or the left? It should go to the right. It is larger than 7. There is room here, so we'll place it. We'll place the 3. No room here. Should it go left or right? It should go left. No room here. Should it go left or right? It should go right. Is there room? Yes, there is. We'll place it here. So that's our binary tree. So we dropped these guys. I don't remember if it was Price is Right or Let's Make a Deal, where they had that game called Plinko. Remember that game? Where you,
That was Price is Right.
Price is Right. You have this coin you drop in here at the top, and it kind of bounces around until it just lands into one of the little cubbies at the very bottom that told you how much money you won or something like that. Or for maybe it was an envelope or something like that or whatever it was. So this is kind of like that. We drop something onto the top of the tree, and the very first thing we drop on the top of the tree, that becomes our root node. Well, I guess technically this is the bottom of the tree. Remember I told you our trees are upside down, when we think about them. So the very first thing we dropped on here was the 5. We didn't have to ask any rule stuff. He just, hey, you're the first guy here. You're the root of the tree. All right. And then each additional thing we dropped on here, we didn't have room for it in that location. We had to ask which side does he go to and then place him as we could. All right. So this is a binary tree. Now, did it matter the order I set these things, that I added these things to the tree? Would it produce different trees if I added them in different orders?
Yes.
Absolutely. And that's where it goes back to what we talked about here with the AVL red-black trees, these self-balancing trees. So these guys are kind of binary trees on steroids. So they're binary trees that have one additional step after adding. So after we add something, we would ask the question, is this tree balanced? It just happens to be that we have a pretty nicely balanced tree here. The depth of the left side is within 1 of the depth of the right side. So we wouldn't do anything special. But if we started getting leaves that, after one more here, we're within 1. If I had another one here, so let's just do a couple more 1s. So a 1, 1. Now we have a tree that's out of balance. So what we'd have to do is then employ a rebalancing algorithm to rearrange this portion of the tree to get these guys back into balance. And that's going to deal with, left shifts and right shifts, depending on how it's out of balance. It's like a whole algorithm thing. It's actually a pretty complicated data structure. If you do a search for AVL trees, it kind of talks about the different rotations you would do. But ultimately, what would likely happen is this 3 would take the place of this 2 here. So we kind of do like a counterclockwise shift, which would then allow these 1s to fall in underneath that, getting us back up 1 level, rebalancing the tree. That type of thing is what goes down. We're not going to be looking at that. That's more for performance. Know it exists, whatever, blah, blah, blah. But for our world, we're going to be fine with a binary tree, and we'll just take what we get. All right, so if it's out of balance, so be it. It just won't search quite as quick, but it'll be fine. It'll be better than Shadi's file IO. All right, so this is our binary tree. Now, we have different ways of traversing. Traversing a binary tree. we have something called in order, pre-order, post order. Now, in order is going to be the one that's most useful for us. Pre-order and post order have more to do with database, underlying implementation stuff, but we'll cover them at the high level here, but you'll see pretty quickly why in order makes sense. So for all of these, each is relative to a node. So in order, a node will visit, well, let's just put it, we're going to say left, then myself, then right. That's in order. So if I'm a node and I'm traversing myself, I will first visit my left child, who will then traverse himself in order, who will then introduce, his left child in order. We'll walk through this and you'll see it. But after I've finished visiting my left child, then I'll visit myself and get my value. Then I'll visit my right child. That's the order in which these happen. Pre-order says I visit myself first before I visit the children. Then I visit left. Then I visit right. Post order says I visit myself last. Left, right, myself. Okay? So there's the different ways we can traverse a tree. Let's go through each of these. We'll do post, then pre, then in order. All right, so post order. Post order says we visit ourselves last. All right, so I'm at this node right here, the 5. I'm going to visit myself last, so I'm going to visit left, then I'm going to visit right, so on and so forth. Now, this is actually an example of recursion, what we're going to see here. So the first thing I do, remember I said that traversing a tree comes from the perspective of the node itself. So when I say I'm going to visit my left child first, I'm basically putting this particular call to post order on hold. I'm going to this child, I'm saying, I want him to visit himself post order. And what does he do? He visits his left child first. That puts that second one on hold. Now this guy is visiting his left child. He has no left child. Then he visits his right child. He has no right child. Finally, he visits himself. So we get a 1. Then we bounce back up because we're done with the post order on this guy. We bounce back up. Now we visit the right child of this guy. He has no left. He has no right. So he finally visits himself. So we get the 3. Then we're done with the post order visiting of him. We bounce up. Finally, we visit ourselves at this level. That's our 2. Then we bounce back up here. Finally, this guy can visit his right child, who goes to visit his left child, doesn't have one, who goes to visit his right child, who goes to visit his left one, doesn't have one, goes to visit his right one, doesn't have one, finally visits himself. That's an 8. Then bounces back up. This guy now can finally visit himself. That's a 7. Bounces back up. This guy can now finally visit himself. That's a 5. All right, so that's traversing this tree using post order. Now, like I said, that doesn't have an obvious use for us right this second. That's more for database optimization and breadth first and depth first search stuff. So I'm not going to really talk about that. Hopefully they talk about that in the database class to a certain extent. Okay, so now we'll go to pre-order. Pre-order says we will visit ourselves first and then our left and right child. All right, so we start here at the top. We're going to visit ourselves pre-order. So I visit myself first. Then I visit my left child, who visits himself first. Then he visits his left child, who visits himself first, who then visits his left child, doesn't have one, who then visits his right child, doesn't have one. So he's done. We bounce back up. We visit our right child, who visits himself first. Then he visits his left child, doesn't have one, visits his right child, doesn't have one, bounces back up. We're done here, bounces back up. Now we visit our right child, who visits himself first. Then he visits his left child, doesn't have one, visits his right child, who visits himself first. Visits his left child, doesn't have one, visits his right child, doesn't have one, bounces back up, and we're done. So that is pre-order traversal. Now, the one that'll make sense to us in order traversal. Okay, in order traversal says that we will visit our left first, then ourselves, then our right side. Okay? So, when you come in here, we're going to do an in order, says visit left. Come here, do an in order, says visit left. Get here, do an in order, says visit left, nothing there, then visit ourselves, 1. Then visit our right, nothing here. So we're done here, jump back up, visit ourselves, then check right. Visit our left, nothing there, visit ourselves, visit our right, nothing there, bounce back up, bounce back up, bounce back up, visit ourselves, go to the right. He visits his left, nothing there, visits himself. That's the 7. Visits his right, visits his left, nothing there, visits himself. Visits his right, nothing there, bounce up, bounce up, bounce up. And what do we have as our final value here? All our numbers in order. That makes sense? So this is what is produced by doing an in-order traversal of our binary tree using a binary tree data structure and using its special sauce here where values to the left of a node are less than or equal to it and values to the right are greater than it. So the fact that we added these nodes to this tree in this specific way then gives us this special thing here where we can traverse in order and get our stuff in numeric order, alphabetical order, depending on what you're storing, that kind of stuff. That makes sense? So any questions on what we just did there with post, pre, and in order? With in order should be the one that has an obvious benefit for us. The other two should be like, I believe those have uses for some things, but it's not obvious to us right now. And that's okay. That's where I'm going to leave it for us. All right, so now, Shadi, you said you're going to implement one of these for us real quick?
The binary tree?
Yeah.
I mean, I can give her a shot.
What time do we want to get out of here?
Yeah, we better not.
All right. So it actually, just like our linked list when we did that initially, you know, so one of the reasons I like explaining the stuff the way like this, where we start off by looking at the theoretical side of it, then we implement it, is almost always as we're going through this, it's like, okay, well, yeah, this all makes sense, but our initial gut feeling is that, well, this seems to be pretty powerful, and this seems to be kind of, you know, I don't know, that there's a lot going on there, and just this whole phrase up here of where am I at here? Of nonlinear linked data structures, that just sounds scarier. This has to be hard to implement, right? That's a lot of times, you know, inexperienced programmers walk into situations like this when something sounds hard or sounds complex, they assume the implementation must be hard. Okay, and binary trees are actually a classic example of something that is really pretty easy to write, and you're gonna, I think, see how simple the implementation is. So we'll do our node here first. And our node here is very, very, very similar to what our nodes look like in linked lists, with one exception. This is a non-linear linked data structure, so we will have up to 2 children instead of exactly 1 child. So we're going to have a payload And our first example here, we'll do ints, and then after break, we'll come back and we'll write this in terms of some objects. Maybe like itinerary objects is kind of where I'm thinking I'm going to go with this, but we're going to think about a simple one with just integers for right now. So we're going to have a payload. We'll call this it's going to be an int payload. And then we're going to have a node left child, and we're going to have a node right child. All right, that's going to be our node class. And then we're going to have a binary tree class. And this guy is going to have a node called root. Okay, and then we need to have the ability to add value or something like that that takes an int payload as a parameter. All right, so let's go write these guys into, we'll just use our current project and we'll slap it in there. So I'm going to right click here. I'm going to create a Java class. Now, because I think do we already have nodes in here, or did we get rid of those? Let me cancel this real quick. Yeah, we already have a node in here. So let's call this a B-tree node, just to keep things simple. So we'll call this guy a B-tree node. All right, we decided this guy is going to have a private int payload. This guy will have a private node left child and a private node right child. We'll have our constructor for this guy, public B-tree node. It's going to take in an int payload. We'll set this dot payload equal to that payload. And then when a B-tree node first comes into existence, he has 0 children. So this dot left child will be equal to null. This dot right child will be equal to null. All right, now we need to go ahead and give ourselves a getter for our payload and then getters and setters for our left and right child. So we'll do that little right-click, generate, delete, flippy magic. So we'll generate a getter for payload. And then we will generate a getter and a setter for left and right child. All right. So that is our B-tree node. Then we'll come in here and we're going to create our binary tree. And we decided a binary tree will have a private node called root. We'll have a public binary tree constructor. It'll take no parameters, and an empty tree has a root node that's set equal to null. And then we'll go ahead and we're going to create a public void, what do I call it? They call it add value. Takes a int payload as a parameter. Very first thing we'll do is we'll create a brand new node. Node n is equal to, it's not a node, it's a B-tree node, right? Passing it that payload. All right, so there is my node that I want to put into the tree. So now I ask the simple question, am I dealing with an empty tree? If this dot root is equal to null, then this dot root is equal to n, and I'm done. Yeah, this guy is a B-tree node. This dot root is equal to null. Okay, so if this guy is nothing, that means the dude I just created is the top of my tree. I'm done. Else, my tree has stuff in it. My tree has stuff in it. I need to go ahead and place this guy into that tree. All right, so I'm going to pause here for a second. I'm going to go back to my B-tree node. And we're going to, where's my B-tree node? This guy. This guy is going to have a add node function that takes a B-tree node as a parameter. And this guy is called a B-tree node now. So we'll go ahead and write this function. This is from a node's perspective. So we're going to say add node. This takes a B tree node n as a parameter. It's going to return nothing. And his job is to place this node. All right, so what's he going to do? Well, he already knows that his position is taken. So n cannot have this guy's spot. So we want to ask if this guy should be to the left of, we want to know, does n belong left of myself, left of this, or does it belong right of this? So if n.getPayload is less than or equal to this.payload, if the node I'm trying to add is less than or equal to myself, I want to add it to my left. So then I'll say if this dot left child is equal to null. If I currently don't have a left child, then I found a home for you. This dot left child is equal to n. What do I call it? Oh, I had these guys as nodes as well. My left and right child are B tree nodes. All right. So nice if I had done that before I generated all my crap. Have to update all my getters and setters now, because it's not nodes, it's B tree nodes. I actually could have done it with refactoring, but that ship has sailed now. Okay, should be good now. So if this guy belongs to the left of myself, and I currently do not have a left child, he becomes my left child. Otherwise, this dot left child dot add node n. Ask my left child to deal with them. Else here, if he doesn't belong to my left, onto the left side of me, he belongs on the right. So if this dot right child is equal to null, if I don't have a right child, I'll say this dot right child is equal to that guy. Else, this dot right child dot add node n. That's it. That's a binary tree. So we can come out here to our main activity. I know we're doing a bunch of crap here right now. Let's just throw this stuff here at the top. So I'm going to go ahead and create a binary tree called BT. This is going to be a new binary tree. And then we'll add some stuff to it. We'll use the values that we had. I don't remember the exact order we added it, but just so we match up. So we added a 5, then a 2, then a 1, then a 7, 8, 3. 5, 2, 1, 7, 8, 3. It should be close enough. One, 7, 8, 3, 2, 1, 7, 8, 3. All right. So we'll go ahead and that should work. We can go ahead and well, I'll just leave it. It'll work. So now what we want to do is we want to implement our 3 traversal methods. So we'll go into B tree or binary tree. Oh, my tree has stuff in it. That's if the else, I'll say this dot root dot add value or add node n. So that starts the process. If I have the empty tree, just set the root to that guy. Otherwise, add the new child to my single root node. And he starts that magic by calling add node here. He tries to place him. If he can't place him, he passes him on to his correct child for his correct child to place him. So you see how this is kind of pseudo recursion? Recursion is when a function calls itself from within itself. Technically, I am calling the add node method of btree node, but I'm calling it of a different instance of btree node. So in here, this call to add node is this is add node, whereas this call to add node is owned by this.left child. So once I get to his copy of it, it'll be this, and so it's the same method but owned by a different instance of the btree node class, which is why I say it's kind of pseudo recursion. All right, so in our binary tree, we'll go ahead and we'll do a public, why don't we do this? Public, we'll just keep it self-contained for right now. Visit in order. We'll have a public void visit post order. And we'll have a public void visit pre-order. Something like that. And then what we're going to do is we are going to teach our btree nodes how to visit themselves. You look back at our thing here, traversing a binary tree. In order says check left child, then myself, then right child. Pre-order says myself, then left, then right. Post order says left, right, then myself. So we're going to teach a btree node how to visit himself in each of those three ways. So public void visit. You know what? Let's make this look kind of cool. I'm going to have it actually return a string. That way we can kind of see the pseudo recursion thing. So we'll say public string visit in order. And this guy will return. Okay. Now he's supposed to do what? He's supposed to visit in order means visit left, then visit right, then visit, now visit left, then himself, then right. So I'm going to create a string called answer here. Start this off as the empty string. All right. Then I'm going to, remember we're supposed to visit our left first. So if this dot left child is not equal to null. If I do have a left child, then I'm going to say answer is equal to answer concatenated with. I'm just going to build up a string for my answer so it looks kind of like what we created here, like the string 132.875, something like that. I'll just put spaces between them instead of commas, but whatever. So we're going to say answer is equal to answer concatenated with, I'll just put a space here, concatenated with this dot left child dot visit in order. Whatever returns from visiting the left child in order. After we visit the left child, we're supposed to visit ourselves. So we'll say answer is equal to answer concatenated with a space, concatenated with this dot payload, myself. Then if this dot right child is not equal to null, answer is equal to answer concatenated with a space concatenated with this dot right child dot visit in order. Okay, so I visited the left child first if there was one. Then I visited myself. And I visited the right child if there was one. Each time I built up this string called answer. So in the end, I'm going to return answer. All right, so that is visit in order. Now if I come back here to my binary tree, and for visit in order, I go ahead and I do a system.out.println, and I'll put my some asterisks in here. And I'll concatenate it this dot root dot visit in order. Technically, we should probably ask the question if this dot root is not equal to null. So as long as I'm not dealing with the empty list, then do this crap. So what am I going to do? I'm going to call visit in order of the root. And what will he do? He will visit things in order. Create an empty string. Try to visit the child, left child. Tack it on to that string as we're building it on. Here's like that pseudo recursive call. This is the left child's version of visit in order. Build up our whole string answer, ultimately return answer. We'll come out to our main activity here, and I'll say bt.visit in order. And actually, if we want it to look a little nicer here inside of our binary tree, we can put in order or something like that. All right, and we'll go ahead and run this guy. Bring up my logcat here. I'll do ... So there's my in order 1, 2, 3, 5, 7, 8. Got some extra spaces in there because of how I did the concatenation, but that's us visiting the elements of my tree in order. Then we can go write the post order and pre-order. So we'll go into our B tree node. I'm actually going to copy this guy. So this is for visit pre-order. Pre-order says we visit ourselves first. Something like that. We'll still have some extra spaces, but we'll just leave it alone. All right, so pre-order says visit ourselves, then our left, then our right. Post order says visit our left, then visit our right, then visit ourselves. So here in our binary tree, we'll steal the same thing here. So this is post order, this is pre-order, so this is post order here. So we'll visit post order, and this is pre-order. We'll visit pre-order. Now we do need to make sure we go into our B tree thing here. Because we did this copying and pasting stuff, a common mistake, and I was about to make it, is visit pre-order means that we need to visit pre-order for all of these. So we're doing ourselves first, then left, then right. Just make sure when you do left and right, since we copied and pasted, you update how we're visiting the left child and how we're visiting the right child. We're visiting these guys in pre-order now, not in order. Similarly, down here for visit post order, we'll visit left child, but we're visiting him post order. We'll visit right child, also post order. Then we'll visit ourselves and return the answer. And then we'll go ahead and show bt.visit post order, bt.visit pre-order. And we should get strings that look pretty similar. I think I put the stuff in the same order as we did before. Is it running? There's in order. Looks like it croaked. Oh, hold on. Is it in order? Does
Had
it?
asterisk space in. And that's what you were searching for in the logcat.
Oh,
That's why they weren't showing up.
yeah. Thank you. Yeah. So there's in order. There's post order. So 132.875. 132.875. And then pre-order 521.378. 521.378. All right, so there's all of our different ways of traversing a binary tree. When we look at our, forgetting about the visit, in order, pre-order, and post-order functions in here, our binary trees here look pretty similar to our binary tree nodes look pretty similar to our linked list nodes, with the exception of instead of having a single next node, we actually have two next nodes, a left and right child. And then our binary tree itself also has the head of a list, has the head of a tree. We call it the root. Just like a stack, we call it the top of the stack. And our add value is kind of like add front, where we create the node. We say, hey, if I'm dealing with the empty tree, we'll just add it right to the root. Otherwise, I'll ask that guy to add the node using the binary tree special sauce, which is this add node guy here, which just says if the guy I'm trying to add should go to my left, can I directly put him to my left? If yes, do it. Otherwise, ask my left node to deal with it. Otherwise, he must go to my right. Can I directly add him to my right? If yes, do it. Otherwise, let the right guy deal with it. So pretty simple logic for creating a, pretty useful data structure. So questions about what we just did there for writing it. What we're going to end up doing after break is converting this guy to work for itineraries and or airports for our next assignment. I'm not giving you an assignment over Easter break. I just wanted to bring us up to that point before we went on break so we had a good launching point. So having said that, any questions about any of the stuff we did here? Going once, going twice.
I think we're good.
All right, so did everybody study for the quiz?
Yes, sir.
What did you study? Tell me how long you studied.
I actually watched your video and I heard how you called me lazy and I wasn't going to watch the video. So.
You still seem concerned that you missed a quiz.
Yeah, I was super concerned because I didn't watch the video and then, and then the quiz. I was like, what the heck?
So hold on, we got you did watch the video, but then you didn't watch the video.
I watched it after the hackathon. So.
I got you. So when you went to study for your quiz, you watched, then you realized that I got a free bottle of Coke Zero.
Yep, pretty much.
Yeah, so I was happy with that. But so how long did you study? You just watch one video?
No, I watched the videos and then I just kind of worked through it and stuff.
So would you say you spent at least 3 hours studying?
Yeah, probably at least.
At least. Anybody spend longer than 3 hours?
4.5.
4.5. Anybody longer than that? I would have expected 12, 13 hours of studying. All right. So I'm not going to give you a quiz because I don't want to grade a quiz. And I think, well, I think I posted a thing. I've been dealing with tests and crap the last couple of days, so I don't feel like grading a quiz. So in any case, but good news is I think I posted all my stuff came back fine, so I'm good.
That's
so,
awesome.
Yeah, so it's I guess the idea is that if you, because I've had a sinus infection for like a month since I got back from my last trip. I guess when you have an infection that long and they keep pumping drugs and stuff into you, you end up getting inflammation from the drugs themselves. So that was causing inflammation in my sinuses, which was putting pressure on my optic nerve, I guess, which was giving me vision issues. But that's gone away. They put me on these prednisone steroid stuff for 10 days, and I'm already call it 90% better. But in any case, I leave for Mexico tomorrow, so I can get sick again. So that's positive. But yeah, so no quiz, but I'm glad you all studied for the quiz. What we will do when we come back from Easter break is we will incorporate this binary tree lesson into our airport travel hacking thingy one way or another. And I do promise you, you will have an assignment that first week back. So don't get used to 2 weeks without assignments. But I am glad everybody participated well in the hackathon. It seemed like all the teams did a really good job. And particularly, I think those of you, well, all of you who were on teams kind of shined in your own way. So I was pretty proud how this particular class engaged in the hackathon. So I guess that's good. So I will attempt to find a way to provide hackathon-based extra credit somewhere in the course, whether it's points on the final or something like that, in lieu of this quiz. So I'm rewarding you for the quiz, but also rewarding you for hackathon participation, that you all did a good job. But I'm also threatening you it's going to be a hard assignment when we come back from Easter. So it's prepare yourself emotionally, whatever. Okay, so any questions, comments, concerns, anything before we call it quits until after Easter? Okay, so I will get this video uploaded so you have it, so you can go back and review the binary tree stuff. Maybe, when you start doing your next assignment, I'm guessing you're probably not going to watch it before then. But anyways, I'll get it up tonight, and I am accessible. I'll have Slack and email and all that stuff while I'm gone. So if you are working on anything or have questions or whatever, I'm available. I'll be in Mexico. All right, I will talk to you all when I guess I'll talk to you when I talk to you.
Happy Easter.
All right, you too.
Good night, all.
Let's see. How do I do? Oh, I think I just do this.